some vocabulary. There is a voltaic cell, and this is the electrochemical cell that produces electricity spontaneously. So here is like a setup of a battery here, and I'll explain this a little bit more in a little bit, or in this podcast though. If electrical current occurs spontaneously, so basically it produces an electrical current when you set up the battery, this is called a voltaic cell. Okay, and that's all your batteries. So if you plug something, since a battery produces electrical current, it causes something to go. It's a voltaic cell. Electrical current is the flow of electrical charges through a wire. Okay, so anytime you have electrons flowing, this is an electrical current. Okay, in this case, we're going to have them flow through a wire. An electrochemical cell, on the other hand, is one that the generation of electricity through the wire connecting to half cells. Okay, so with these, the electrical current to drive a non-spontaneous reaction. So this is where you use an electrical current. It needs electrical current so you can drive a non-spontaneous reaction. So basically, voltaic one produces electricity spontaneously, and an electrolytic cell kind of needs a little bit of energy to create the electricity. And I wanted to show you, here's kind of what one looks like when you're putting them together. You literally have, we were balancing those half reactions before, on the podcast before, and we had some copper too, maybe in there, some zinc solid. Well, you see in here, here's, some copper in here. Now at the bottom and down here is some zinc. And you literally just put them in the beakers and you're going to connect them by a wire. And when you connect them by a wire, you create this battery. So let me show you here. A voltaic, sometimes they call it a galvanic cell, is an electrochemical cell that produces electrical current from a spontaneous chemical reaction. So you're going to have a spontaneous reaction that produces electricity, okay? A second type is the electrochemical cell, sometimes they call it electrolytic cell. It consumes electricity to drive a non-spontaneous reaction. Okay, so this one just produces it through a spontaneous reaction. This consumes it so then it can drive a non-spontaneous. And make sure you see the difference between those. Okay, and I wanted to also show you, here it is. Here's that picture, except here's in color, so I think it looks prettier. Okay, so do you remember these little half reactions right here? Here's just an example with the zinc and copper. And I think the first example we did was balancing these half reactions. So here they are balanced, okay? Here's the oxidation, here's the reduction reaction. And what you do is your half reactions, you literally put these in different beakers. So you're gonna put your zinc over here, put your copper over here, and you put it in solution. And then you're gonna connect them by a wire, okay? And this is how a battery occurs. Okay, this one over here is your anode. Why is this your anode? This is how I like to think about it. Yes, the zinc was oxidized. So you see it went from zinc 0 to zinc 2+. So this was oxidized. Okay, but if you think anode, I think of something negative. Okay, look at this. Think about the product. You see that it produced 2 electrons, and electrons have what? A negative charge. So in this oxidation reaction, you produce 2 electrons with a negative charge, and that's why it's called the anode. So because you're producing electrons, okay, in your product. Okay, the cathode is where the reduction occurs. Now I know that again sounds kind of weird because you think cathode positive. Okay. But look here, you do not produce electrons, okay? It needs electrons for this reaction to occur. Do you see that it needs the 2 electrons for this reaction to occur? So what happens? Your anode, it produces 2 electrons, you see right here, okay? Those electrons flow through the wire, creating a current that's needed in the cathode over here, okay? So there's this constant flow of electrons from the anode to the cathode. Okay, now if this, there's going to be, basically you need to balance your charges here, because if the charges just stopped, okay, so we have what's called a salt bridge here. You see we have the negative charges going in here and the positive going over here. Now, if this salt bridge wasn't here, literally this battery would go once. You know, all of the electrons would flow over here to the cathode to kind of neutralize it, and then it ends. Well, we don't want that to happen. We want to keep pumping negative electrons over here, and you know, this needs to stay positive, so we need to keep pumping them in here. So that's what the salt bridge is sort of there to balance everything so it keeps going, okay? And that's the point of the salt bridge. Anyway, so let's go over a little bit more vocabulary. You have your half cells, and those are your half reaction. Those are your anode and your cathode. You're connected by a wire, so you have a flow of electrons. Your anode is where the oxidation occurs. Remember, oxidation means you produce electrons. And your cathode is where the reduction occurs, which means you need electrons for the reaction to go. And the electrons flow from the anode to the cathode, because remember, they're produced over here in the anode, and they flow into the cathode, which needs them. And then the salt bridge is there to balance the flow of charges between the anode and the cathode. And you have one, I put one on there, a podcast to go over a little bit of this setup a little more. Okay, you're going to have an electrical current, and that's measured in amperes. So this is just your coulombs, which is a measure of an electrical charge per second. So this, a current is just how many charges per second, okay, flow. The potential difference here is that you're going to measure the difference in the potential energy. So what we're looking at is cell potential energy. So the voltage, you see joules per coulomb. So this is the voltage is just the energy you get from the charge. Okay, so energy per charge, and that's a volt, and that's what we're trying to get. So you're going to see the cathode needs so much energy to occur. Okay, needs so much energy for the reaction to occur, and the anode produces so much energy. So the difference between them is your cell potential, and that's in voltage. When we're looking at 1 molar concentration in 1 atmosphere, we're looking at this standard cell potential. And we're just going to concentrate on the standard cell potential in this. There's a calculation where you have a non-standard cell, so if you have a different molarity or a different pressure there. But we're just going to focus on the standard cell potential. Okay, and notice, remember, anytime something's at standard state, like the Gibbs, free energy, or entropy, you have this kind of degree sign there. There's cell notation. So from here on out, you're going to see your cell notation like this. Okay, notice these are your two half reactions. So your zinc going to zinc 2+. So anytime you see how that arrow, or not the arrow, the line that's kind of like saying an arrow, and your copper 2+ to your copper. Okay, the one written first is always your anode. See, this is the oxidation, so it went from 0 to 2+. And remember, it produced electrons. And this is the right one's always your cathode. And you're separating them here. This indicates a salt bridge. This is how it's always written. And the next thing we're going to do in the next vodcast is look at how do we put them into that cell notation.